Okay guys, today we're going to be covering section 2.1, which is going to be on tangent and velocity problems. And just a heads up, I make mistakes sometimes. I hate recording. As you'll probably see as you watch this or whatever. Anyways, let's go ahead and get started. So the first thing we need to do is define what a tangent is. So a tangent to a curve is a line that touches the curve. So to be touching just means you have to intersect, means you actually, like, these two lines have to, be at the same point at the same time or whatever. And the second thing we should say is it has to have the same direction. And the same direction just means, we kind of preserve like what the curve is doing at that point. So a few examples would be like if we looked at this point right here, and a tangent line to that curve would look like this. Because here the line will go through this point and we'll try to preserve what the circle is doing. If you look at the circle right here, it's going to be if you look at the circle right here, you kind of see that the curve is still trying to, get the same kind of slope that the circle has at that point. So another example that we could do, it would be like if we just take a curve like this, make it look at a curve, not a curve, we could look at a point right there, and the tangent line would look kind of like that. So it'd have to go through this point, and it would still try to get the idea of what, like, the kind of behavior what the curve is doing right at that point. And then another example would just be like on this curve would be like this, where again this line, which in this case is going to be a tangent line, is going to be going through this point and still trying to still change at the same rate that the curve is. So the thing is, like, the problem is how do we actually find what these tangent lines are? So, like, for example, if we just get rid of this tangent line, and then we could just say we call this x, and call this y, and we call this point P, and we can say, and this curve can be f of x. We want to know what is the line, and what equation can we find for this tangent line. So that's kind of where we have to use something else. We have to use some other motivations. We have to figure out, maybe there's a better way. Maybe we could approach it somehow. And that's kind of the idea where secant lines come in. So the first thing we need to do is define what a secant line is. Give me 1 second to find the notes. All right, okay. So a secant line is a line that touches a curve in two different spots, or 2 different points. So these points have to be distinct and they have to intersect the curve, and it doesn't matter if it's 3 points, 4 points, 5 points. It could be 100 points. It just has to be more than once. And that's the important thing about secant lines. So again, we could let's use some quick examples. So on a circle, we could say, let me do red. If we do the points right here and here, a secant line for these points would be like this. And maybe if we go back to the curve as again, we can do like a typical example I did last time. Oh, looks like the graph is in red this time, guys. Let's just say this is our curve. And then here are our points. Then a secant line to this curve, or with respect to this curve, would be like this. So one of the things we should notice that if we talk about this in the xy plane, say if this is x and this is y, then again we can define this curve to be f of x. It doesn't necessarily have to be f of x, it doesn't need to be a function, because circles aren't functions, but that doesn't matter so much. We could call this point P, we call the other point Q, and then again, like, these values for P and Q, P will equal to x1, y1, so y, and Q will be equal to x2, y2. So, and this is just because, these are actually points on the xy plane. Like we can actually put this stuff in a setting that we're actually used to. So we can call the secant line. We say the secant line will be denoted by, we'll say like, I hate this stupid Apple Pencil. All right. So the secant line, I'm going to use, so this notation right here, which I'm doing, which is like a semicolon, or maybe a colon, I don't know, with an equal sign usually means like denote. It's a way to say like like a defined, or like a definition. So we say that's equal to PQ. And that's just a way to do the line. Typically you could see like in geometry, you might see the notation with the bar to kind of indicate the line. In this case, I'm just going to write PQ because I'm lazy and I don't want to write that bar. And we say the slope of PQ, which we're going to denote that by MPQ. M is, like kind of standard what we see for slope, and PQ because it depends on that line. We should note that if Q or P change, then MPQ will also change. And that's kind of why we write the PQ there. It's because it's fixed. I guess you guys just saw an email I got. Whatever. So the thing is, it's like here is 2 points. The secant line is 2 points. Oh, whoops. I hate that. All right, okay. So the secant line actually has 2 points. We have P and Q, and we actually have a slope as well. And because of that, we can actually find the secant line. We can actually find it, and we can use, point slope form for that. So we can say like secant line, looks like we're working in yellow. I'm gonna change that back to black, make it a bit more clear. So the secant line will be defined by, like, we can not define, but we can describe it using the equation y minus y1 is equal to m times x minus x1. And note we can do, like y1, x1, or we could do x2, y2. It doesn't really matter as long as we use the same, like point. Oh yeah, and one other thing I kind of forgot to mention, I don't know how I forgot, is that MPQ, the slope of the tangent line, like because I've defined it, I use a notation, but I haven't specifically told you what it said. MPQ will be equal to y2 minus y1 over x2 minus x1. And that's the same thing as just, y1 minus y2 over x2, it's not x2, x1 minus x2. And the order doesn't really matter because it's kind of arbitrary. You can relabel them if you want. It doesn't really matter. The idea is we can actually define what the secant line is. This line, we can call it known. Pretend I'm writing the word known. Oh, I hate when that happens. All right, so we can actually know what that is. So now, why am I talking about secant lines? That's kind of a good question. I'm gonna pretend someone in the audience asked that. Why are we talking about secant lines? So this is gonna be I'm gonna be drawing you guys a picture. It's gonna be an annoying picture, but it'll give you kind of an idea of why we're doing it. So let's just start over here. Let's start with a big old graph, and then like this. So we'll call this x, call this y. Let's define this curve like this. So here will be our p, and we're gonna fix it, and let's just say fix p. So what this means is we're not letting p change at all. We're not gonna let it vary. We'll say it has an x value. Okay, all right. So let me get an x value. We'll say this is equal to x equals a, and this will be f of a. And we can define this curve to be like f of x. So this point p will just be equal to a f of a. So it's known. It's fixed, it's not going to change. And the thing that we want to find is going to be this tangent line. You want to know how can we define that. So this is kind of where we have to use secant lines for. Oh, whoops. Apologize. All right. Okay. So if we, let's just say we start with this point Q. The secant line, and then let's just say, not the secant line. Yeah, let's just go and start with that. We can do the secant line for this. Will just be, I'm going to try to use blue for that. And then just go all the way through like that. So it'll just be a line connecting these 2 points. So then what would happen, let's just say, what would happen if we took this value? We'll just say we call this point Q as an x value of just x, keep it kind of arbitrary. You can call it a different thing if you want, but this point Q then would be x f of x, because it just means the points on the curve. The question is like, what we want to observe is, what happens if Q is like, what if we move Q right here? Or then what if we move Q right here? And what would happen if we just keep on moving Q closer and closer to P? And what would happen to the secant lines? So already if you want to compare what these, the red line and the blue line look like in this case, the tangent and the secant line, they don't actually look too similar at this point. But let's kind of observe what happens whenever we move Q closer to P. Damn it, I hate this. All right, so then let's go through here. This will be one secant line as Q moves over. Here it will be like this. And then the next step will be like this. And then this step will be like this. So I don't know if it's, kind of too easy to see or anything, but what's happening is this curve right here, as the Q moves over, the secant lines is going to be approaching the red line, or we're going to be approaching the tangent line. And the same thing here. It's going to be like approaching that tangent line. Let's go and erase that. So what this means is that, if we have a secant line and we have P and Q are really close, so let's just say, like if we look at this point right here, and we're going to draw the secant line for that, it's for that specific point. Then we'll see that it's actually pretty close to that tangent line. And that's kind of the idea of how we find tangents. So let's try to define what's actually going on here. So again, let's clarify what P is. So P will be equal to a f of a, and Q will equal to x f of x. And we said earlier that, we'll define the lines to be PQ, the secant line to be PQ, so the line will be secant. And we say the slope, which will be equal to MPQ. Well, like what we said earlier, is just going to be, y2 minus y1 over x2 minus x1. What that will give us is actually, Lord, it's going to be f of x minus f of a all over x minus a. So I don't know if you know, but this is actually an equation. This is a value. The slope right here depends on x. So we could model this. We could plug it in the values together. But this actually, the idea is, what's going on is, I should probably write it to erase it. As Q gets closer to P, then MPQ gets closer to the slope of the tangent line. And we're just going to call that slope, I'm going to say in parentheses, call that M. So the way we can do this in terms of just like the way we can write it in terms of notation, because mathematicians are lazy bastards, we'll say as P goes to Q, or vice versa. Oh my lord. They said iPads are fancy and Apple Pens are fancy, but man, they suck. Just kidding. So as Q goes to P, we will have MP of Q, the slope of the secant line will approach the slope of the tangent line M. So far what I've given you is a bunch of letters. I gave you basically just the alphabet, and the question is, where's the math at? Sure, there's some equal sign somewhere, but where is the actual math? Where is some numbers that I can work with? So let's actually start with an example. So let me just kind of separate it off. All right. So the first example we're going to work with is going to be, let's just say, let a curve be defined by y is equal to 4 over 2 minus x. And we want to find the tangent, so, and p is equal to 3, negative 4. So we want the tangent of y at p. Or instead of saying y, you could say the curve. It doesn't really matter, as long as it's kind of clear what you're talking about. So the thing is, again, that we need to talk about a secant. So like I said, in this problem, we had a secant line. So we need a q. So what we're going to do for our q is we're going to let q equal to x and 4 over 2 minus x. And this right here is just known as, like, you could say the graph, but it's just known as like a point on the curve. That's what it means to be like on a plot. It just means your x value and this will be your y value. So by choosing q to do this, or be this value, we can, kind of let it be arbitrary. So now, so the value that we want to, we want our q to approach, or our x to approach, really, because our q depends on x. We want x to go to 3. Or in this case, saying x goes to 3 is, we want to approximate 3 with, really, like, values that are really close to 3. So first off, let's at least get the slope first. Because, the thing that we need to find a tangent line is just, I'm going to do it off right here. It would be, we need a slope and a point. And that gives us a line, because this will just be y minus y1 equals to m times x minus x1. So the thing that we need is the slope. And what I've told you up here is that mpq goes to m. So now we have to just figure out what mpq is. And this is kind of the part where you can do it, there's like a few different ways to do it, but I like to just write out the equation for it. So we do mpq, which we said is, like y1 minus y2 over x1 minus x2. So this will just be, let's see, 4 over 2 minus x minus 4 all over x minus 3. And this, because this is our point, like, not p. This will be our point q, this will be our point p. And this will be like the y value. This is our y value right here of p, q, and this is the y value of p, and this is the x value of q, and this is the x value of 3. Well, of p, my bad. So now we want to do is, like, saying this right here is not really rigorous at all, but, we're going to get there. I promise. So one of the things that we're going to do first is, like, what we said here is, as q gets closer to p, then mpq gets closer to the slope of the tangent. Or say, as q goes to p, mpq goes to m. So in order for us, find what these values are, in order for us to say, like, q goes to p, so we note that this is the same thing as saying we need to let x go to 3, as I kind of said right here. So the values that we can use to, kind of give us an idea of what's going on are just values that are really close to 3. So let's do the x value. And let's do a chart of mpq. This will be the other chart. All right. So kind of like I would have said is we have to be close to 3. So the values that we're going to choose, I'm going to write them in a different color now. So the first one would be like a number that would be close to 3. I think your first guess or my guess would be 2.9. If you said like 7 or 4, you probably want to question yourself. Not really. So And then some other points we would say, like to say 2.9 and 3, like those are close, but you can find an even closer number. In this case, the even closer number would be like 2.99. And even then, 2.99 and 3, still a bit of a gap. So we can go a bit closer if we want. 2.999. And we can do this, as much as we want, but the idea here is just to get this idea that as we get closer to 3, MPQ will get closer to M, which is, like the slope of the tangent line. So for this will be for values less than 3. So here is less than 3. And here will be greater than 3. And that's just an idea of kind of how we're approaching it. So this will be like 3.1, 3.01, 3.001. So we can take these x values and plug it into right here. Because, this is basically just an equation for the slope of the secant line in terms of x. So what's going to happen when we plug in, 2.9? What we're going to get is 4.444 and repeated. It's going to keep on going. Then for 2.99, what we get is 4.0404 and so on. It's going to be 0, 4, 0, 4, 0, 4, and so on. Then 2.9999 or whatever, it's going to be 4.004, 004, and so on. And this kind of gives you an idea already what 3 should be. So let's do 3.1. So 3.1 would be like 3.6363, kind of repeating like that. 3.01, that would be like 3.96. 0396, probably some pattern there. I didn't write down all the numbers. 3.001, that'd be like 3.996. And now the thing is that all these values are close to 3, but what are these values close to? I'm going to assume that you guys agree with me and say 4. So 4. Oh man, that's horrible. Let me not do like some mustard yellow, McDonald's yellow, I don't know. In this case, it should be 4. So again, this value right here is actually equal to, this will be equal to M. So this we get, like that way what we're saying really is when P is, or not P, always start with P. Man, I'm writing in yellow again. I apologize, guys. Okay. So we say when Q is close to P, or you could say near if you like, P, which is in this case, like X is close to 3. Because in this case, both Q depends on, X. What that tells us is that MPQ is close to M. Thus, we get that okay, sorry. So thus we get that, the slope of the tangent line is equal to M, which should be approximately equal to 4. And the reason why I say approximately equal to, like, it's kind of clear in these cases that, it's what's really going on, what these values are approaching, but it may not always be obvious. And, that's fine. Like, how do we tell the difference between, 4.00001 and 4? But in this case, we just kind of have to use our intuition to kind of see what these values are approaching. And this is why we say, this would be like an estimate. But in this case, we're just going to assume, instead of, approximately equal to, we just have an equal to. So in this case, that tells us that the tangent line at P, which again was, I think, 3, -4, we'll have slope M, or in this case, have slope 4. So we get that this tangent line will be defined as, sorry guys, So then we'll have, again, like y minus y1, which should be minus 4, times the slope, which will be m, so 4, or whatever, x minus 3. All right, that was weird. And that right there will be the equation for the tangent line. So, and again, like the process that we're doing is, we talked about this idea of closeness. And the question is, like, if you look at this value right here, this is 3.1, but we're still off by a significant number of digits. So we're still like, kind of close. And that's why we still got to be a bit more rigorous on this. But in the meantime, if our functions are nice enough, as it's going to be on your homework for 2.1, we get this intuition of, how this value is, basically equal to 4 is like, one we're allowed to like work on, or we're allowed to actually work with. All right, and that actually covers tangent and the secant lines. So now the second problem that, we have as a section is called the velocity problem. So the velocity kind of problem kind of comes from, like a very natural, thing. Like imagine if you're like driving your car. So let's just say, you got a little car, little wheels. Pretend that's a car. Your car, like you gotta start your car. So when you first get in your car is not moving at all. So let's just try to graph the distance. Like let's just say you're, try to look at the distance versus time. Call this D for distance and T for time. So if you first get in your car, it's not started or anything. You're not moving. So at time equals 0, you move 0 distance. You're not moving when you get in your car. If you are, it's probably not a safe car to drive, or you're probably in a not good situation. So anyways, so let's just say now, you start the car and you're going to like Walmart. I don't know, could be Walmart, could be Target. I don't know where you guys go to in your free time. Could be the clubs. So let's just pretend we're going to Walmart. So the first thing you have to do is, start the car. And then as you, let's just say you're pulling out of the driveway, but you're not going too fast. So the distance you would go would be like kind of smooth. So it would look like this. You're not really like going too fast. But then, you stop for a second to put it in drive, and then you're going, kind of faster. Let's just say you go to a stop sign. So then you have to slow down. And then you eventually kind of turn on the highway where you're now moving like 50 miles an hour. So in this case, now you're moving a lot faster than you would. So you cover more distance in a smaller amount of time. And this right here would be like, how you measure the distance. So this would be like the distance as like a function of time. So some of the notation we might use would be like, I think in this problem, or in a future example, we're going to like S of t is equal to S. Or in this case, it would be equal to like D. So the question is like, we kind of want to know like, what is the velocity? Like if you look at your speedometer at any moment, like if you're looking at the speedometer, if you're at a stop sign, it's 0. And that kind of correlates with what's actually going on because you're not moving at all. And if you're in this, oh crap, not what I wanted. And if if you're in like, this section right here, then like your car is moving. Like you can look outside the window and you're observing yourself actually moving. And that's how kind of like, we know that the velocity here should be positive. Because, you're actually moving some distance. So the question is, like, we can figure out what the average velocity is, but we don't know how to find the instantaneous velocity. How can we find what your actual speed is at any given moment? So the way we write that is like, the problem is, if I could actually, okay. How do we find how do we find the velocity v? I know that's pretty standard to mathematics. If we want to find, velocity v, we just use the variable v at a time t. And note that, just for notation, guys, I usually like to do my t's like this, but if I ever do, like plus, or if I'm only doing like a then I usually just, kind of write it like that. But if you're doing math where you're doing like t, it's try to make sure you're not writing like cosine of like t or like cosine of plus, because honestly that just looks whack. So there's a little pro tip for you guys if you write awful like I do. So anyways, like how do we find the velocity v then? So we do have a concept of average velocity. So we have like, let's say like we have an average velocity, which I don't know if you guys know any like physics or anything, or if you like, ever worked with a problem like this. Say the average velocity, I'm just going to use velocity. I'm just going to put a period there because I don't want to write the whole word velocity. We call that v average. And then because, it's the velocity, but it's the average velocity, but that's equal to the change in distance. We'll say the change in d, which sometimes people will write, as like delta t over the change in time, which is also sometimes denoted as like, delta t. But really what matters is, let's just say we call this point, like, again, kind of going back with like, we're using our distance as a function of time. So we can say, let's call this point A, call this point B, and then this right here will be like a change in time. We'll call that distance, like B minus A, and that will be like our change. We're going from a time A to time B. And if you look at this curve right here, oops, not what I wanted. So then if we look at, if we look at the points on the curve right here, this will be like, this right here will be like f of A, or not, well, not f, because we just said s right here. This will actually be f, no, why am I saying f again? My bad. Be s of A. And this right here will be like s of B. So we define the average velocity of, our car, driving us to Walmart. Will actually be, in this case, it'll be v average will be equal to s of B minus s of A over B minus A. So here, this is, our change in our distance, because we defined, like this y-axis to be distance. So this will be a distance. Like this will be a distance, this will be a distance. And then, so the height of that will be a change in, the distance, and then from A to B will be the change in time. So we find v averages would be s of B minus s of A over B minus A. Again, what this kind of looks like so far is, if you, look back up, kind of looks like the slope of, a secant line, where instead of saying f, instead of saying, like f, why am I, okay. Instead of saying f, now we're using s. That's why I was kind of getting confused earlier, or that's why I kept messing that up. Because what we're really doing is just finding, the slope of the secant line. That's what really what v average is. So if we call like, we call this point right here, call this P, we call this point right here Q, then we'll say, if we go with similar notation as earlier, then PQ will be that line, and what we have is that the slope of that line, this will be the secant. Actually, let me write that more clear. So PQ will be the secant, and MPQ will equal to, in this case, will actually be equal to the average, will be V average, where P is equal to A S of A, and Q is equal to B S of B. So again, this kind of looks weird at the moment, but one of the ways we notice that, like why is this true, is let's just look at what MPQ is. So MPQ will be equal to S of B minus S of A over B minus A, which in this case is equal to the same thing as we had above, so it's equal to V average. So in this case, what this tells us is that the velocity problem is the same thing as like, doing the same thing as the tangent line. Because, what we want to do is try to find what your actual speed is. Well, in this case, it's kind of clear at this point. But we want to find what your actual speed is at this point right here. So again, and the way we do that is by taking average velocities over really short intervals of time. so let me just try to clarify what that actually means. So what we have is like, as Q gets closer to P, then MPQ, which we'll call that, in this case, is our V average, will get closer to M, which is the slope of the tangent line, but for us, that's really our velocity. And that's kind of how we're doing that. So this will be secant. This will be secant goes to the tangent. And in that case, that actually allows us to, figure out what velocity is in terms of the same kind of methods we did last time. So let me just try to depend on an example. All right, let's pull up an example now. In this case, I think for the example, I've got like, actual homework problem we can do. Oh, whoops. Okay, I think this is the one. Looks like we're gonna be doing purple. All right, so what we have is a point P at 3, -4 on the curve. Oh, nope, that's the one I already did. Whoops. I apologize. I think it's, yep, it is this one right here. My bad. Okay, I think I got it. All right, sorry to get myself in. If this thing works. All right, now it's working. Okay. So the first thing we need to do is define where P and Q is. We want to try to find the curve and all of that. So, this problem says if an arrow is shot upward at on Mars with a speed of 56 meters per second. The fact that it says 56 right here doesn't really matter. It just basically changes right there. So its height h. Its height we'll call it we'll call it height h. Is meters per second. Oh no, its height h in meters t seconds later is given by y is equal to 56 t minus 1.86 t squared. Those are just funky numbers we can just kind of ignore at the moment. But that tells us that our height h of t is equal to 56 t minus 1.86 t squared. And what the problem is asking is they want us to find the average velocity on different intervals. So this will be V average. I always say do that. V average on 1, 2. So what this means is that our point P will be equal to, 1 h of 1, and Q will be equal to 2 h of 2. And thus the V average at these points would be equal to your height at h of 2, that's your height at time equals 1, whereas 2 minus 1, which is in this case the same slope as MPQ. But that's just to make it a bit more clear. So in this case, I actually didn't pull out those numbers. Let me do for, okay. Well, that's gonna, whatever value we get here, which frankly I kind of did the wrong number, would be the answer for right here. But let me actually do the problems that I actually have. Let me actually just do one of the parts. So the ones that I have done so far would be 1 to 1.5. So we're going to do this one right here. And all the other problems are going to follow similarly. All right. So we'll see. One of the things that you kind of need so important, if you do I think on the test you don't really need to specify, but make sure to kind of clarify where you're taking your average on. So we'll say V average on 1 to 1.5. Otherwise, if I ask you what the average velocity you've been doing, you can ask me well, what period of time? Are you talking about your whole life? Are you talking about just today? Are you talking about this whole week? Are you talking about just your trip to Walmart? I got to clarify what time we're working with. So in this case, we have is this going to be equal to h of 1.5 minus, it's not really denoting, but h of 1.5 minus h of 1 over 1.5 minus 1. And all I'm doing now is just plugging into the formula. So we have h of 1.5 means we just plug in 1.5 into the function. Let me actually change it to a nicer color. All right. All right, okay. So this will be equal to 56 times 1.5 minus 1.86 times 1.5 squared minus, oh, whoops. Whatever, I'm gonna write it a bit down. So this will be 56 minus, well, times 1 minus 1.86 times 1 squared all over 1.5 minus 1. And this point, you can just kind of plug it into a calculator. And the main idea, all I did right here was just, plug in 1.5 into the function. And this right here, which is h of, 1. All I did was just plug in the values and evaluate them. And then if you plug into a calculator, what you're going to get is 51.35. And again, this is, velocity, so it's meters per second. So the answer I would have here is 51.35. So I can do this with the other examples too. So like if I do on 1.1, then what I'll get is, let's see, it was 52.094. Man, that is tiny. 52.094. For 1.01, we'll get is 52.26. And then for 1.001, what we get is 52.278. So now, kind of like what we did last time is, at least in the secant problem, is that we used we used the MPQ to kind of guess what, P was. Because, at some point whenever, in this case, when P is, really close to Q, we'll say, you could say P is approximately equal to Q. Then you get MPQ is approximately equal to M. That's basically kind of what we're doing. So in this case, what this is saying is that V average is approximately equal to V whenever we have our, our delta time is approximately equal to, 0. Or in this case, it's just saying that our time interval right here is, the distance between the time or distance between time. How much time has passed? It's just 0.001, so it's pretty small. So basically these 2 points are close to each other. So in this case, we just take 52.278. We can just round it to the nearest, 2 decimal places, as it kind of asks right here. So we just get 52.28 meters per second. So again, let me clarify what's going on again. Let me just kind of go through the problem. So the problem asks us to find, it gives us an arrow shot upward with a speed of 56 meters per second, and it gives us a height as a function of time. So we know the average velocity is just, it's just on a certain time interval will just be, it's, the height of it at a specific time divided by, the change in the height divided by the change in time. And we can kind of use that to kind of guess what a velocity would be, the speed of the arrow would be, at equals 1. And here, just note that here I'm actually saying velocity because I like to say velocity. It's kind of, but in this case, it's a synonym for speed. It's basically the same thing. So if I say velocity and it's kind of confusing you, if I, instead of saying, when the problem says speed, just kind of know that's literally the same thing. All right, and then one last example, because this one is just slightly different. All right, so this one's going to be pretty similar. In this case, we have a cyclist, someone just riding their bike, and after 0 seconds they've gone 0 meters because it's kind of obvious. After 1 second they've gone 1.5 meters. After 2 seconds they go to 5 meters. After 3 seconds they've gone 10.6 meters. And the problem is asking us to find the average velocity for each time period. And again, the V average, I'm going to use that with just arbitrary notation now instead of using A, B. We'll say on A, comma B, and try to like, you know, if you guys don't like this AB notation, I apologize, but that's something you'll just have to kind of get used to. Because the thing about using, you know, just letters like A and B is we don't have to specify. We're not using any of the properties. If we look at 1, 3, 2, 3 through 5, those are all numbers. If we just let, you know, A and B be arbitrary, just, you know, letters, then that uncovers all these cases right here. So just be mindful of that. But this will be equal to, you know, our S of t, well, S of b actually, minus our S of a over b minus a. Where these values right here will be our S of b or S of a or whatever we need them to be. So if we want to find v average on, let's say, 2 to 3, and that's just going to be equal to its height at, you know, at 3, so it'll be 10.6, and then its height at, you know, 2 minus 5, and then the distance between the time, or, you know, how much time has passed, which will just be 3 minus 2. So this will just be 5.6 divided by 1, which is equal to 5.6 meters per second. So in this case, our answer here will be 5.6. And I'm not going to do all the parts because, you know, if you guys can understand what I'm doing here, then clearly you can do some of the other parts. So let me just do another example just real quick to show you. So V average on, let's say, now let's do this one right here, 34. That'll just be equal to 17.3 minus, now it's going to get 10.6 over 4 minus 1. Oh, not 4 minus 1, my bad. 4 minus 3, which is equal to 1. We get 6.7 meters per second. And that's what happens if you just like plug it into a calculator. So the problem is asking us to find instantaneous velocity at t equals 3. And note that what we're not actually doing right here is we're not actually approaching, you know, our time steps are not getting smaller. This is like 2, this is 1. And like how do we like estimate the instant velocity given what we have? So we know that, you know, if we just draw a little curve on the side, we know that, you know, like if you look at this point right here, say find this curve right here, the point right here, even though this will be like, you know, this will be like 2, this will be 3, and this will be 4, even if we know, like, you know, the secant lines are not, you know, not necessarily the same, nor are they really close to 3, but we know that if we average them, they might give us a good estimate of what the secant line is. Well, not the secant line, but what the tangent line is at 3. All right, so ignore all that stuff. It's like to mess it up on me. So basically what we're doing here to find t equals 3, you should know that basically 3 is the midpoint of, you know, 2, 3, and 3, 4, or like the common point, I guess you could say. So this right here will be equal to, you can call it V, equal to V average on 2, 3. You can do plus the V average on divided by 2 on 3, 4. In this case, it's just going to be equal to 5.6 plus 6.7 divided by 2, which gives us 6.15 meters per second. So this answer here will be 6.15 meters per second. And that basically gives the instantaneous velocity at time equals 3. And note that this is an estimate. It's not perfect, but it's a pretty good guess. And so these problems are kind of weird to get used to at first, especially if we haven't really defined truly what it means to be close to something. You know, like, is this like a true method? Like, how close do we have to be? And that's not something we have to worry about right now, just in this section. So I think you guys are pretty good. So good luck on the homework. See you next time.